Aloha, Richard Halverson here. This is ITS388AL, and we are in week 10. And so this week we're going to start chapter 7, integer arithmetic, and that includes the shift and rotate instructions. And so today I'm going to cover the PowerPoint slides. I'm going to cover about half of them, and that takes us right up to the point where we can start and do programming assignment 6. So let me open up the slides here, and we're in chapter 7, integer arithmetic. In this chapter, we're gonna cover shift and rotate instructions, some applications, multiplication and division instructions. And that'll take us up to the point where we can do the assignment. The assignment is it's a modular arithmetic problem where we're finding the greatest common divisor between two integers. And then the next video we will do the assignment, or start you out with the assignment. And then the last video for this chapter will cover the extended addition and subtraction and some other features of the Intel 86 microprocessors to help us do decimal arithmetic and packed decimal arithmetic, and you'll see what that is. All right, so shift and rotate instructions. First, we're going to define the difference between logical shifts and arithmetic shifts, the shift instructions, arithmetic shift instructions. There's rotate instructions, and you'll see the difference between those. And then these are shift involving two memory locations, and so it's these. You would use these instructions if you wanted to do multi-word shifts, where you're shifting large extended values stored using multiple words in memory. Okay, so a logical shift so here we're shifting all of the bits to the right. And so it's pretty clear that bit number 1 goes into bit number 2 and so on. And but the question is, where does the first bit that gets shifted out, or the lowest order bit gets shifted out, and what gets shifted into the highest order bit? Well, for a logical shift, a 0 gets shifted into the highest order bit when you're shifting right, and the lowest order bit gets shifted into the carry flag. For an arithmetic shift, you're doing this sign extension, so you want to make sure that that the highest order bit stays the same. So in this case, the highest order bit stays the same, and then the rest of the bits are shifted just like a logical shift. And so here's the shift left instruction. This is shifting left now. It performs a logical left shift on the destination operand. And so this is the destination operand. So we're either shifting a register or memory. And then this value is the number of bits to shift. Let's see, let me find. All right, I just wanted to confirm CL is what I thought. It's the lowest order, the lower half of the C register. You know, it's not CX, it's not AX, it's not AH, it's not AL, it's CL. So you can put the number of bits to shift in the CL register. It's not you. I've never used that. I just always shift a certain number. Anyway, so when you're looking at shift left, we're actually multiplying by 2. And so, for example, let's say that the byte has the value 5 in it, 0, 0, 0, 0, 0, 1, 0, 1, and we shift left once. Let's say this is the DL register. and we shift left once, and so then it looks like this, and it's 10. So shifting left n bits is like multiplying the operand by 2 to the n power. So if you want to shift, if we want to multiply by 4, we shift left twice. The shift right instruction is like dividing by 2, sort of, except for it's a logical shift, so we're not doing sign extension. But in the highest, the 0 goes into the highest order bit, and the lowest order bit goes into the carry flag. So here's an example where we're moving the value 80 hex into DL. Well, no, it doesn't. No, it doesn't need to be 80 hex. It's 80, the value 80 decimal into DL, and we shift right. We shift right 1, and that's going to be like dividing by 2. And if we shift left shift right 2 more times, it's like dividing that by 4, and so the result is going to be 10. The arithmetic left shift and the arithmetic right shifts are the same, except for, well, the left shift is identical. The arithmetic left shift is identical to the logical left shift because, because you don't have to worry about sign extension. But the SAR, the arithmetic right shift, is not the same as the SHR because you're doing sign extension, you see. Okay, so here's some examples. Let's see, does my pen work? Yes, it does. So let's do the first one here just to start out with. I gotta do some light color. How about this color? I'm just gonna do white. All right, so we're loading into AL 6B, so that would be 6 is 0, 0, 1, 1, 0, and B is A is 1, 0, 1, 1. And if we shift right 1, that's this direction, let's shift this direction. So it's going to end up being, and it's a shift. So it's logical shift. It's not SAR. So it'd be 0, 0, 1, 1, 0, 1, 0, 1. Because this goes here, 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 and this goes here, and this goes off into nowhere, and a 0 goes in here, and so this is 35, which is what this shows here. And here we're doing, this is like an arithmetic right shift. So if we do this one, we start out with AL is equal to AC. So it would be 8C. AL equals 8C is 1, 0, 0, 0. C is 1, 1, 0, 0. And you're doing an arithmetic right shift once. So it's going to be a 1 is going to get, this is going to go, it's a right shift. So this goes away. This goes 0, 1, 1, 0. And then, let's see, no, wait a second. That's this, that's this, that's this, that's this. 0, 0, 1, and then a 1 gets shifted in. So it's 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, which is C6, which is what it shows there. So anyway, that's some examples of shifting. The rotate left instruction, we're rotating now. What happens is the highest order bit gets wrapped around and stuck into the lowest order bit. See, and the highest order bit also goes into the carry flag, but it also goes into the lowest order bit. instead of 0 going in there, or instead of the other carry going in there, this one goes in there, the highest order bit. For rotate right, they all go down. They all go down once. The lowest order bit that goes into the carry, but the lowest order bit also wraps around and goes into the highest order bit. So you can try those out with these two examples, and you can do that. Rotate carry left shifts each bit to the left and copies the carry flag into the least significant. So we're going this way. We're going left. And so all the bits get shifted up. It's like multiplying by 2, except for whatever was in the carry bit gets shifted into the lowest order bit. And the rotate carry right, it's like dividing by 2, where it's going down. They're all going down. The lowest order bit goes into the carry flag, and the carry flag comes around and goes into the highest order bit. And you can try out these examples. Okay, this is a 3-operand instruction. It's shift left destination, and it shifts a destination operand a given number of bits to the left, and the bit position. The bit positions that are opened up are filled with the most. See, we're going left, so we're going this way. So the bits that open up at the bottom are filled with the higher, most significant bits of the source operand. So they're filled with this one. So these all get shifted left, and then when the ones that open up are filled in from here. So it's like we're shifting this whole thing left once, and they're all being shifted in. The source operand, that's the source operand, is not affected, and this is the number to do it. So for example, here we're just doing 1. We're just shifting once, and this destination is AL. This is AL, low order A. This is low order B, and so they all get shifted left. It's this direction, and so it looks like this. The highest order bit of the destination goes into the carry flag. They all get shifted left once. The lowest order bit, though, gets its new value from the source operand, BL. Here's another example where we're shifting 4. When we shift 4, it's like we're shifting a whole hex character. So here we had 9BA6, and then the source was AC36, and so they all got shifted up once. B, A, C, A. See, and these stay the same. We have a shift right instruction, which does the same kind of thing. The destination is in this case is AL, and the source, see, destination was loaded up with 11000001, and the source is the 0011101. It's this thing, and it gets shifted as you'd expect. And another example is you can do, if you want to shift the whole nibble, or you want to shift the whole hex character, you can put a 4 there, and you see it looks, the destination is not affected. The source, only this, no, I'm sorry, the destination, the source is not affected. This is the source. And it's only the destination that's affected. This is the destination, this is the source. Okay, you can do some examples here. Next, we're going to look at some applications. And we're going to go through these pretty quickly. There's shifting multiple double words, binary multiplication, displaying binary bits, isolating a bit string. So shifting multiple double words, sometimes programs sometimes need to shift all the bits within an array, like through a whole array. Like for example, if you when you're moving a bitmapped image, graphical image, for example, and so the following shifts an array of 3 double words 1 bit to the right. We start by, let's say we've got a big array here, and we start by shifting the highest order double word right, left, right, okay, and then we want to do rotate right, including the carry, and this so it's we use the carry bit to hold the intermediate data when we're going from instruction to instruction, and we can only do one at a time because the carry bit is only 1 bit long. For binary multiplication, we can it's also called a shift add, where we're going to multiply 123 by 36. 36 is actually this in binary, 100100, and so we take this 23 and we shift it left 3 positions, and that's this one. So if it's a 1, and this is just regular multiplication, but we're 1 times 1 is 1, and 1 times 0 is 0. Since it's a 1 here, then this is copied down into this position, shifted left 2, 1, 2, and then shift left, 1, 2, 3, 4, 5, and you're copying this down here. That's the same thing here, and then you add. You just add them up. 0, 0, 1, carry the 0. Wait a second. Oh, this is 1. This is 1. This is 0. 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 1 is 1. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 1 is 1. 11. Carry the 1. 0. Carry the 1. 0. Carry the 1. 0. Carry the 1. 1, 0, 0, 0, and the result, and you convert that back to decimal, and you end up this. So sometimes if the operands are such that when they're converted to binary, there's very few ones, the multiplication can end up being real fast. See, this is only like 2 add operations, and that's because the multiplier, when converted to binary, only had 2 1 bits. Now, if you were doing something like 31, multiplying it by 31, that'd be a lot more difficult, because 31 is like 1, 1, 1, 1, 1, and if you're going to do so that would be 5 things that you have to add. So you'd have 5 instances of this all shifted left once, and so that's more expensive. Anyway, that's how binary multiplication works. And so here's more of an explanation, and that is that any number can be you can factor any binary number in the powers of 2. So this is actually what you're doing. You take EAX here. You take EAX times 36. That's actually EAX times 32 plus EAX times 4. EAX times 32 plus EAX times 4. And EAX times 32 is shifted left 5 times, and times 4 is shifted left twice. So see, this is how you do it. This is the number. This is the multiplicand. Multiplicand, you put in an EDX, and then you put the multiplier is going to be 32, and you shift that twice. And anyway, so and then you add them up, and you end up with the result. So you can go through this, and here we're multiplying by 26, and it's going to be 3 additions. Shift left once, shift left 2 more times, and then shift left 1 more time. This is an example of displaying binary bits. You can look at that. In the old days, MS-DOS would the date field was like actually packed into 2 bytes. The year, it's 2-digit year, 2-digit month, and 2-digit day. And there's some shifting and stuff that went on to here to extract out, to pull out the different date properties. All right. Last in this video, we're going to cover the multiplication and division instructions. And back before the thing that the 8086 offered, before the 86 series, there was the 8080 series, 8008 series, 4040, and 444. But before 8086 or 8088, there was no multiplication or division instruction. There was just adding and subtracting. And so, but higher level languages that were implemented, or the way you would do multiplication or division, is you would do it manually, like I showed you, like we just saw how to do multiplication. It converted to shift add, and division, you can do the same kind of thing. It's harder to keep track of, but you do shift subtract, and that's how you do division manually. And then with the 8088, they introduced this multiplication instruction. They still didn't have a division instruction. That came later. But with multiplication, you can do division like the way we learn how to do division by hand in grade school, where you guess and you multiply and so on, and you can do that by subtracting and so on. But now we've got division, multiplication, division instructions, and so let's look at these. The multiplication instruction, there's unsigned multiply and signed multiply, taking care of the whether numbers can be negative or not. And the formats are like this. For an 8-bit, well, it doesn't. There's a multiplicand and a multiplier. So 5 times 2 equals 10. This is the multiplicand. The multiplicand is the first one, the multiplier is the second one, and the product is, of course, the result. And so when we're doing a MUL instruction, the multiplicand, this thing, is always the accumulator, the A register. If you're doing 8 bits or 16 bits or 32 bits, it's always the A register. The multiplier is the source. That can be a register or memory. And then the product, the result, goes into the A register. You notice that the result can be twice as big. I mean, if you have two bytes, if you multiply 2 8-bit bytes, the biggest it can be is 16 bits. The result can be 16 bits. So we see that the product result. Let me see if I can change the color here. The product result here is twice the size of the multiplicand. Here we're using the lower order 8 bits, and the result is going to take both the lower and the upper. Here the multiplicand is 16 bits, 16 bits. The result is 32 bits. Uses the AX register and the DX register as the upper byte, the upper 16 bits. And for 32-bit operands, we're using both the EAX and the EDX register. And the 64-bit multiplication instruction uses the RAX and the RDX registers. RAX. The multiplicand and the multiplier is this. So here are some examples. We're going to multiply this by this. We load the first value into the AX register. We can just multiply the multiplier, as we can reference that directly, and the result is going to be in AX dx spread across that way. The carry flag indicates whether or not the upper half of the product contains anything. So in this case, the carry flag is going to be 1 because the upper half contains something. And for 32-bit operands, here we see, here we're doing this times this, and we end up with EDX, EAX, and the upper is 1, 2, 3, 4, 5, 6, 7, 8, and this is the lower. And so the carry flag is 0 because the upper doesn't have anything. So you can do this example. And this example is a 32-bit one. The IMUL instruction is like the multiply instruction, except for it does signed values. And same kind of format and everything. It's just that it preserves the sign of the product by sign extending it. So it's smart enough to know that if you multiply a negative by a positive, you get a negative. You multiply two negatives together, you get a positive, and two positives, you get a positive. And there's a 64-bit mode, of course. And here's some examples. Here we're multiplying by a negative number, so the result ends up being a sign extended negative number. You can verify this. The division instruction, this is as far as we'll go today. It's an unsigned divide. Instruction performs either 8-bit or 16-bit or 32 bits. A single operand is supplied, either a register or a memory. And so the dividend, it's like, 5 over 2 equals, 2 equals 2 with a remainder of 1. Yeah. So the dividend is the 5. The divisor is the 2. The quotient is the resulting 2. And the remainder is 1. So if we're doing 5 divided by 2, we would put 5 in the AX or the AX register, or that's for an 8-bit number, so it takes up 2 bytes. The dividend can be twice as big, but the divisor is the memory size that we're talking about. So the divisor for an 8-bit divide is going to be up to 8 bits, but the dividend can be 16 bits. When we're doing a 16-bit operation, the divisor can be up to 16 bits, but the dividend can be 32 bits, two 16-bit registers together. And if we're dividing using a 32-bit number, the dividend is going to be up to 64 bits. So we need 2 of these E registers. And the result, the quotient, goes back into the EAX, and the remainder takes up the upper half. So you notice EDX is where the upper byte, the upper word, double word in this case, of the dividend was, and also you're using the full AX register when you're dividing, and the quotient goes in the lower half, and the remainder goes in the upper half. So in our assignment, we're going to be using the division instruction, and we're going to be doing mod operations. You see, this is exactly the dividend divided by a divisor. If we're doing integer division, the quotient is going to be, you know, it's going to be an integer, and then there's going to be a remainder in most cases. And so this is just the mod, and this is the integer divide, and this is the mod. So we're interested in this remainder. We're going to be dividing, and each time we're going to grab out the remainder as a result of the mod operation. And so here's some examples. And so let's so that's there's signed integer division. We're gonna use in our assignment, we're gonna first see if we're dealing with negative numbers, and if we are, we're gonna take the absolute value of them. So we're gonna be using this division, this div example, the div instruction. All right, so if we take a look at the assignment, we see it is it's this greatest common divisor, and I give you the algorithm. I give you a C++ version. You might not know C++, but you know C#, and you can see it's the same. So we first taking the greatest common divisor. Okay, so the greatest common divisor is the biggest number that divides evenly into two integers. And so so an example is, let's say you've got 15 and 25. Let's see, do I have something? Okay, so let's say you have, let's see, does this work? Okay, you have let's say you have 25 and 15. Okay, these are two integers, or these are two integers, and we want to know what the biggest number that divides evenly. Well, it's 5, because 5 times 3 equals that, and 5 times 5 equals that. So the biggest, this isn't a very good example. How about 169 and 39? Okay, that's going to be, it's 169 is 13 times 13, I think, and 69, this is 13 times 3. 13 are prime, these are prime numbers, these are prime numbers, so that's as far down as we go. But anyway, that's so this is an algorithm which allows you to figure that out. And the way we do it is we continually take the mod. So we start with X and Y, and this is like 25 and 15, and we take 25 mod 15, and we get an N, and that's the result. That's the mod operation. So if we use a division instruction, this is going to be you know, the DX register, or whatever, the EDX register. This is going to be the EAX register, and we're going to use probably EBX for the Y. So we do this operation, and then we're going to move what was Y over into X, and with the resulting N is going to be moved into Y. So Y is going to go over to X, and N is going to go over to Y. And we're going to keep on doing that while Y is greater than 0. So once Y becomes 0, then we're done, because we're doing a mod operation where we're modding in evenly, and the mod result is 0. See, and the resulting is the one just before it, which ends up being X. So that's the algorithm, and what we're going to do is we're going to take this algorithm and we're going to create an assembly language version of it. All right. So so that's what I've I'm covering. So that's it for today's video. And next time we're gonna do. We're actually gonna do. I'm gonna start you out with the assignment. Thanks for watching.